In this video, we're going to talk about section 10.3, parametric equations in calculus. Our objectives will be to find the slope of a tangent line to a curve given by a set of parametric equations. Second objective will be to find the arc length of a curve given by a set of parametric equations. Our third objective will be to find the area of a surface of revolution in parametric form. We're going to need some of our trig identities for this. So I have this trigonometry review sheet from the textbook over there for us to make reference to later when we need that. Let's go ahead and go back to a problem from last time where we had an example. Consider the path followed by an object propelled into the air at an angle of 45 degrees. Recall the parametric equations last time where x of t is equal to 24 root 2 t for x of t. This was our v naught was equal to 48 feet per second as part of the problem. I forgot to write that down. And y of t is equal to negative 16t squared plus 24 root 2t. And we found the implied domain here that t had to be between 0 and 3 root 2 over 2 because it started over here at 0 on the ground and it landed over here at time equals 3 root 2 over 2 when x was 72 over here on the ground, and that this was a little bit more than 2 over here. So somewhere over here, around 1 is its maximum. It's a little bit later than that. But we're going to talk about this. I'm going to say this initial angle right here, I'm going to put a subscript to 0 on it to show that its initial angle of 45 degrees. We have these other angles that will be over here that we see the angle decreasing here as time increases, and that has to do with the x component is staying constant, but the y component is being affected by this negative 16t squared. Let me just show you a couple equations here from physics that will be important for you with these parametric equations. So x of t is going to be equal to v naught, this number right here, times the cosine of this initial angle. They'll call that alpha in physics, but I'm just calling it my initial theta right here. And y of t is going to be equal to 1/2 g, the acceleration due to gravity, t squared, plus v naught sine of my initial angle, t here, excuse me, v naught cosine theta sub 0 t, and this is v naught sine theta sub 0 t, and then this is plus your initial position y here, which in this case was 0. I guess you could add x0 here as well. So usually we are starting at 0, 0. But this is a constant rate of change here. In the x direction, it's perfectly linear. It's going to go just like this. So for each of these triangles, the length of this side should be the same. And it should be the y piece that is starting off kind of big, then getting smaller, and then getting bigger in the negative direction like that. And that's affecting this angle. We're measuring the angle from the positive x-axis here. Positive angles going counterclockwise, then negative angles going clockwise. We don't go counterclockwise to go all the way around to that angle. We go to the closest way to measure the angle, even if that's going to be a negative angle. So the slope of the tangent line at t tells us about the angle of elevation of the object at time t. In this example, if I have a positive angle, I have a positive slope because my slope is actually going to be tan theta here. Negative angle will give me a negative slope. All right, that's enough intuition there and setup for this. So let's talk about theorem 10.7, parametric form of the derivative. Sorry that you're gonna have a while for it loading. I've got a lot of inking on this. I erased a lot of it already, and we'll rewrite it as we go along, but that's gonna cause stuff to have to load up as I scroll the pages here. If a smooth curve C is given by the equation x equals f of t and y equals g of t, then the slope of curve C at xy is dy dx is equal to dy dt divided by dx dt, such that dx dt is not equal to 0. This is just the chain rule, is all that is. So we're having to use the chain rule to evaluate derivatives for equations that are given in parametric form. So let's look at this example here, that if x of t is equal to sine of t and y of t is equal to cosine of t, that means my dx dt would be cosine of t, and my dy dt would be negative sine t, and my dy dx as an equation of t is going to be dy dt is negative sine t divided by dx dt is cosine of t. Sine over cosine is tangent of t, so dy dx is going to be negative tangent of t. Let's go ahead now and talk about the curve given by the equations. X of t is equal to the square root of t, and y of t is equal to 1/4 of the quantity t squared minus 4. And t has to be greater than or equal to 0 because of the domain here for x of t. That means x has to be greater than 0, and that means that the smallest this can be is going to be a -1. And then it can get bigger and bigger and bigger from there. All right, so recall we can use the second derivative to draw conclusions about concavity of the graph. If we want to find first and second derivative here, we would take the derivative of the derivative, and we'll talk about how to do that here with the chain rule. So we already know that dy dx is equal to dy dt divided by dx dt. Let's write this kind of horizontally, like so. If I want to find d2y dx2, the second derivative of y with respect to x, then I'm going to take the derivative with respect to t of my dy dx that I just found, and I'm going to divide that once again by dx dt. So let's go ahead and do that here. And then we can evaluate what's going on at 2, 3. I've gone ahead and solved already for you to tell you that at 2, 3, time is 4, that we knew that the square root of 4 is what gave us 2, and I plugged 4 in here. 4 squared is 16. 16 minus 4 is 12. 1/4 of 12 is 3, and I checked it out, and time is going to be 4 there. So let's go ahead and look at what dx dt and dy dt will be. X of t is square root of t is t to the 1/2, and y of t is 1/4 t squared minus 1. So dx dt is equal to 1/2 t to the negative 1/2, and dy dt is equal to 1/2 t. So dy dx in terms of t is 1/2 t, or t over 2, divided by 1/2 square root of t. So this is going to be 2 square root of t over 2 is square root of t, or if you prefer, t to the 1/2 will work just as well. So now that I have that, d2y dx2 is going to be the derivative of this with respect to t. Divided by dx dt is those are the same thing. This should be 1 because this equation for dy dx came out to be the same thing as x. So let's go ahead and figure out at dy dx at the point here where t is equal to 4. That's what we said. And we have the square root of 4 is equal to 2. So we have a positive slope. Since this is positive, and we are definitely concave up. Right? It's important to notice that parametric equations can define plane curves that loop around and cross themselves. We saw this in the last section, that parametric equations can describe graphs in which y is not a function of x. So it's possible that a plane curve may have more than one tangent line at a given point. Consider the next example. The parametric equations given below describe a special graph called a prolate cycloid. This prolate cycloid crosses itself at 0, 2. The graph of this function and the tangent lines are on the next page. Take a look at that. This is an example straight from the textbook. If you want to look in the textbook as well and follow along, x of t is equal to 2t minus pi sine of t, and y of t is equal to 2 minus pi cosine of t. So we're going to need to find dx dt, and that's going to be 2 minus pi cosine of t. And we're going to need to find dy dt, and that's going to be derivative of a constant is 0, and negative sine t times a negative pi is a positive sine t, like so. So my dy dx is going to be sine of t over 2 minus pi, this is pi, sine of t, pi sine of t over 2 minus pi cosine of t. And we're at 0, 2 on the graph. I need to think about where that is. So this one's hard because it's got a t there and a t there. It's easier to solve this one for where 2 minus pi cosine of t is equal to 2. So subtract 2 from both sides. It's It's cosine of t equals 0. Let's look on our unit circle over here. Cosine is 0 at pi over 2 and negative pi over 2. So t1 is equal to negative pi over 2. t2 is going to be positive pi over 2. And we're going to see that that's what we want because we want a, we'll see the picture of the cycloid in just a second. So dy dx when t is equal to negative pi over 2 is equal to pi times sine of negative pi over 2 over 2 minus pi cosine of negative pi over 2 is equal to pi times sine of negative pi over 2 is a negative 1. 2 minus pi times cosine of negative pi over 2 is 0. So this is a negative pi over 2 minus 0 is 2, or a negative pi over 2 for my slope. My dy dx when t is equal to pi over 2 is going to be pi times sine of pi over 2 over 2 minus pi cosine of pi over 2 is pi times 1. Pi over 2 is right here. Sine value is right there. 2 minus pi cosine of pi over 2. Cosine value is right there. Is going to be equal to pi over 2 minus 0 is 2. So now I want to find the equation of the tangent lines. So I have case 1 is slope is negative pi over 2. X is equal to 0. Y is equal to 2. So I'm going to use my point slope form. Y minus y value is equal to m times x minus my x value. It's going to be y minus 2 equals negative pi over 2x. Y is equal to negative pi over 2x plus 2. And then my second case here, it's going to be my slope is a positive pi over 2. My x value is still 0. My y value is still 2. And so I have y minus 2 is equal to pi over 2 times x minus 0. Y minus 2 is equal to pi over 2x. Y is equal to pi over 2x plus 2. Let's see how we did. So there's our picture from the book. There's the cycloid right there that we're interested in with x is equal to 2t minus pi sine t. Y is equal to 2 minus pi cosine t right here. And at the point 0, 2, we have two different tangent lines, one coming from this direction and one coming from that direction. And that they are given by the equations here of when t is equal to pi over 2 and when t is negative pi over 2, we get these two equations of these tangent lines right there that we found. All right, let's move on and let's talk about the idea of arc length. Recall from chapter 7.4 that the formula for the arc length of a curve C is given by y equals h of x over the interval x naught x sub 0 to x sub 1 is lowercase s is equal to x0 to x1 of the square root of 1 plus h prime of x quantity squared dx. And we can write that h prime of x as x naught to x1 square root of 1 plus dy dx squared with a dx on the outside of the integral there. If C is represented by parametric equations, x equals f of t and y equals g of t, such that A is less than or equal to T is less than or equal to B, that I'm on that closed interval A to B. And if dy dx is equal to f prime of t, and that's positive there, then s is equal to a to b of the square root of f prime of t squared plus g prime of t squared. So let's go ahead and look at this in parametric form. Basically, what we've done is we've evaluated this interval right here, changed it into parametric form, and gotten this instead. So we'll write this as probably a to b of the square root of dx dt squared plus dy dt squared, and then with a dt on the outside. That's probably how I'm going to write it. In fact, there it is right there. There's the theorem. The smooth curve C is given by x equals f of t and y equals g of t, such that C does not intersect itself on the interval of t is between a and b inclusive, except possibly at the endpoints. Then the arc length of C over the interval is given by s is equal to the interval from a to b of the square root of dx dt squared plus dy dt squared dt. And that can also be written as f prime of t quantity squared plus g prime of t quantity squared inside the square root sign dt. So let's go ahead and when applying the arc length formula to the curve, we need to be sure that the curve is traced out only once. If we're just trying to find the arc length for one cycle, that sometimes we can accidentally sketch the curve out multiple times. It will trace over itself, and we need to be careful to not do that. For instance, the curve given by x of t is equal to cosine of t and y of t is equal to sine of t. That would be a circle here. Actually, the unit circle can be traced once on the interval of 0 to 2 pi right here. But if I had an interval of 0 to 4 pi, I'm actually going around twice. And that would give me double what I actually wanted my area to be, or not my area, my arc length to be, if I wanted just the circumference around the circle from 0 to 2 pi. I need to be careful with my limits here. So I gave some space here to show that I could have a circle that I could go around multiple times. And each time I'm going another constant multiple of the circumference, and that would increase this arc length. I may want that actually. I may want to know, like in physics, what distance the wheel has traveled when it's made 10 revolutions or something like that. And I may actually want this this upper limit to be something like 10 pi, which would represent, or I said 10 revolutions, 20 pi. So it would represent 10 revolutions, right? And then I could find out what distance the wheel had traveled, which would be the same as what linear distance the car had traveled along the road. If I find this this arc length distance here, that has to be the same distance that the car rolled along the road. So just be careful to know what you want, to read the problem carefully, to know whether you need to restrict your domain here to 1 revolution, or whether you're looking for a total distance of multiple revolutions. And also be very careful. We're going to see this later, but all these definitions here say that it must be a smooth curve here. And so we're going to need to make sure that in our interval that we are integrating on, that we have a smooth curve. So the figure below, you'll see a graphical representation of a circle of radius 1 rolling around the circumference of a larger circle of radius 4. The epicycloid traced by a point on the circumference of the smaller circle is given by the set of parametric equations. X of t is equal to 5 cosine of t minus cosine of 5t, and y of t is equal to 5 sine of t minus sine of 5t. I went ahead and already found dx dt and dy dt for you. That dx dt is going to be a negative 5 sine t minus 5 sine of 5t because of the chain rule. And dy dt is going to be 5 cosine of t minus 5 cosine of 5t. So 5 cosine of 5t. Do something looked wrong there because that's not 0. All right, let's find the distance traveled by the point in one complete trip around the larger circle. Before we do that, let's take a look at what this epicycloid looks like. And I've put these green dots here that weren't there in the picture from the textbook, but I wanted the green points to stand out to you, that there are cusps there, making the curve not smooth at that point. I can't go through there and call it a smooth curve anymore. So I'm going to have to take one of these petals, let's call it. On this looks like a 4-leaf clover or something like that. I'm going to have to take one of these leaves or petals of this flower right here, and it'll be piecewise smooth on that piece right there. And then I can take 4 times that answer to get what I want. So I'm going to just go ahead and put a 4 out here right now to indicate that I want 4 of the distance from 0 to pi over 2. And I have my dx dt equation squared and my dy dt equation squared. And this is going to get real big and real messy real fast. And we're going to need a lot of trig equations for this. So hang on to your hats while we do this. Before 0 to pi over 2. And I'm going to take the square root here. And this is going to be 25 sine squared t. And then we have a negative 5. And actually, let me just get that 25 out right now. So I'm going to pull this, let me do it like so. I'm going to pull a negative 5 squared out from here and make this sine of t minus sine of 5t. And that's going to be squared, plus I've got 5 squared that I'm going to pull out from here and make this equal to pulling out this common factor of 5 and squaring it, since it was inside there, is going to be cosine of t minus cosine of 5t quantity squared. Let's put a dt on the end there. So when I have the when the negative squares, it goes away. So the square root of 5 squared, when I pull the 5 squared in front of everything, is going to be a 5. 0 to pi over 2 of big square root of sine t minus sine of 5t squared plus cosine of t minus cosine of 5t quantity squared dt. All right, now here's where it's going to get real big real quick. but we're going to have some Pythagorean identities that are going to help us. So S is going to be 20, 0 to pi over 2 of, let's just make sure I haven't missed anything. Nope. So square root of, this is going to be sine squared t, and then minus 2 times sine of t, sine of 5t, plus sine squared of 5t, plus cosine squared of t, minus 2 cosine of t, cosine of 5t, plus cosine squared 5t dt. So I'm going to highlight some things for you here that this sine, thought I was going to highlight for you, that this sine squared t and this cosine squared t right there, that they're going to make a 1. And this sine squared 5t and this cosine squared 5t over here, they're going to make a 1 as well. So this is s equals 20 root, or integral from 0 to pi over 2 of root 2 minus 2 sine t sine of 5t minus 2 cosine of t cosine of 5t dt. Now, we need these product to sum formulas that are down here. So we're going to say that s is equal to 20, 0 to pi over 2 square root of 2 minus 2, and then sine u sine v is going to change into 1/2 cosine of u minus v. I'm going to do the big part minus the small part. So 5t minus t. So I'm going to call this one u and this one v. It really doesn't matter with the product. I'm going to call that one u and that one v there, just so I have the big one called u in my subtraction. So cosine u minus v minus cosine of u plus v, like so. And then I have minus 2, and then I have cosine and cosine, which is going to be 1/2 of the quantity cosine of u minus v, 5t minus t, plus cosine of 5t plus t. So s is going to be equal to 20, integral from 0 to pi over 2 of square root of 2, and then this 2 and this 1/2 cancel, and I have minus cosine of 4t minus cosine of 6t, and then I have minus, and then I have cosine of 6t, and then I have plus, sorry, this is 4t, and then I have plus cosine of 6t dt. So let's get that simplified now. S equals 20, 0 to pi over 2 square root of 2 minus cosine 4t plus cosine of 6t minus cosine of 4t minus cosine of 6t, and this zero each other out, and I'm left with s equals 20, 0 to pi over 2 of square root of 2 minus 2 cosine of 4t. So I'm going to be looking at this one up here, this power reducing formula right here, that I want to rearrange this to say that 2 sine squared t, I'll say u, is equal to 1 minus cosine of 2u, where my u is going to be equal to 2t here, because that's what I need to double to get my 4t. So I'll pull my root 2 out as a factor, and s equals 20 root 2 from 0 to pi over 2 square root of 1 minus cosine, like I said, of 2 times 2t dt. I'm going to replace that inside with pi over 2 square root of sine 2 sine squared of 2t dt. So I have another root 2 to pull out, and that's going to be 2 times 20 is 40, 0 to pi over 2 of square root of sine squared of 2t dt is going to be 40, 0 to pi over 2 of sine of 2t dt. So now we need to fix that by multiplying by 2 over 2. So 2 on the inside over 2 on the outside makes this that s is equal to 20, 0 to pi over 2 of a negative cosine of 2t evaluated from 0 to pi over 2. That's the same thing as saying negative 20 cosine of 2t pi over 2, 0. So this is s is equal to negative 20 times cosine of pi minus cosine of 0 is equal to negative 20 times a negative 1 minus 1. S is equal to a negative 20 times a negative 2 is a positive 40, and this is whatever my units are in, and I'm done. That was quite a bit of trigonometry for that problem. I hope you followed all of that, and make sure we weren't given any units here, but go back and check those units. All right, something very related to this, just like we did in chapter 7, is once we knew how to find arc length, we could multiply that arc length times either x or y, and we could get the multiply by a constant multiplier of 2 pi on the outside and find this integral instead. And this would give us the surface area. Same thing here, just that if we're revolving about the x-axis that we're going to multiply by g of t here. We're going to multiply by y. If we're revolving about the y-axis, then we're going to multiply by f of t here, which is our x value, just like we did in chapter 7. So really nothing new there. This is capital S for surface area now, instead of lowercase s for arc length. So let C be the arc of a circle, x squared plus y squared equals 9. That's a circle of radius 3 from the point 3, 0 to the point 3 halves, 3 root 3 over 2. So if we want that to happen, then our parametric equations here, our f of t is equal to our x of t is equal to 3 cosine of t for this circle, and our g of t is equal to y of t is equal to 3 sine of t. We'll learn more if you don't know these yet. The x equals to r cosine theta and the y is equal to r sine theta are the parametric forms of these. They're actually the polar forms of these rectangular things going on, these trig identities. These for SOHCAHTOA, you just multiply by the denominators there. So y is equal to r sine theta, and x is equal to r cosine theta. And we can parameterize the curve that way, just replacing the thetas with t's right now. And I went ahead and found that theta here is going to be 0 radians, and theta here is going to be pi over 3 radians, just by looking here and saying, okay, there's the multiplier of 3 there, so I need 3 times 1/2. I need a cosine value of 1/2. That's at 60 degrees, or pi over 3 radians, and that's going to give me my bounds for integration. Same thing for my y coordinate. It's 3 times something here for sine, and I checked, and root 3 over 2 right there. So that's how I got my pi over 3. All right, let's see. This is going to load up now. That capital S is going to be 2 pi from a to b of g of t root dx dt squared plus dy dt squared dt. And we're using that one because we have revolution around the x-axis. So that's why we made that choice. I'm going to plug my g of t in as 3 sine of t. And I plug in my limits from 0 to pi over 3 for a and b. My dx dt I found was a -3 sine t, and I plugged that in. And my dy dt I found was 3 cosine t, and I plugged that in. I'm going to square both of these, so I get 9 sine squared plus 9 cosine squared. And I see that I can factor out my 9 and get sine squared plus cosine squared, which is just 1. 9 times 1 is 9, is a constant multiple of 3. So I'm going to take this 3 times that 3 is 9, and that 9 times that 2 is 18, and I'm going to take all those constants out front and make 18 pi, integral from 0 to pi over 3 of sine t dt is going to be a integral of sine is a negative cosine, so I put the negative out here with a constant, negative 18 pi cosine of t evaluated from 0 to pi over 3. Cosine of pi over 3 is 1/2. Cosine of 0 is 1. 1/2 minus 1 is a negative 1/2. And a negative 18 times a negative 1/2 is a positive 9. And I know that that's the correct answer for that one as well. So that's it for this video. We'll come back next time and we'll talk about 10.4, which is going to be more about polar equations. We should start talking about polar curves and polar equations. I think we're just going to do some basic definitions there with polar and some polar substitutions. So look forward to seeing you next time for 10.4. See you for the next video.